Okay, hello everyone. I hope people can hear me. So welcome to this invited talks and PODS keynote session. So we are very happy and privileged to have Rajiv Allur with us today. In fact, Rajiv is heroically giving a live presentation of this talk for the second time. So he decided he gave it in both rounds of the conference. So Rajiv is one of the leading figures in the field of computer-aided verification and generally in applications of logic in computer science. He is a professor at the University of Pennsylvania, having received his PhD from Stanford. He then spent a number of years at Bell Labs, where I was very lucky to have been with him in the same department for a number of years. He has contributed to many areas of computer-aided verification with lots of very influential results. He has received a huge number of awards. He's an ACM fellow, IEEE fellow. He got the inaugural CAV award. He got the Church Prize. He had Test of Time Award from Leaks. He was a program chair of CAV, Leaks, general chair of Leaks, and the list continues. He is also known to us in the PODS community. So in particular, from many of you remember his influential work on visibly pushed down languages from the XML days, which was quite popular in our community as well. And today he is giving his keynote talk on synchronization schemas. So please welcome Rajiv Allur.
Yeah, thank you, Leonard, for that kind introduction. And thank you to the PODS organizing committee and program committee for inviting me and giving this opportunity to talk to PODS people. So my background is in logic and computer-aided verification, and I have a lot of intersecting interests with the PODS community. And I'm hoping that this talk, which is about ongoing work on a data model for streaming data, would get many of you interested. So this is joint work with a number of folks at Penn, and you may recognize some of my faculty colleagues who are co-authors on this work, Zach Ives and Walt Tanner. So the context and motivation for this work is real-time decision-making, particularly in the Internet of Things IoT systems, such as smart buildings and network switches and health monitoring devices, where the data is generated at different nodes in a distributed system. And what the system is tasked to do is to process it in a streaming fashion, compute some analytics on the data, and convert the data into action. So in real time, make some decisions so that the system gets influenced, right? So think about like a health monitoring device, which is measuring signals from different devices and then deciding, for example, whether to change a medicine dose or something like that, right? So there is tremendous interest in these kinds of systems, and the requirements are that the decision should be made with predictable latency. And this has generated a lot of interest, not just in the academic community, but also in industry. And there are a number of industrial strength, highly engineered systems for distributed stream processing systems. And Google says that the 10 systems that I see here, these are the ones which are ranked in the order of their popularity. So for example, Google Cloud Data Flow is currently the most popular, and then Apache Flink, which is a system that has roots in academia, is 10th, right? And as you can see, places like IBM and Amazon and Microsoft, they all have their own stream analytics systems, right? If you look at these systems, they focus more on high performance and fault tolerance, and less on programmability. Actually, if you want to program these systems, then the query language that they provide is some streaming extension of SQL, So maybe SQL extended with some windowing constructs. And you can also embed some user-defined functions. And the underlying computation model is many times built on top of the data flow model. So for example, in systems like Flink and Spark, these are very much built on the data flow model. And since the focus is on high performance, the parallelization is a key concern. And typically in these systems, the parallelization support is based on some fixed patterns. So for example, key-based partitioning and relational aggregation. So these are queries that can be easily parallelized, and they're well supported. But there is much one can do in terms of programmability, and that's the motivation for this talk. So let me illustrate the kind of computation we want to do using an example, and I'm going to use this example throughout the rest of my talk. Right? So imagine there is a transportation company which is monitoring events of its fleet of taxis, and in my illustrations, I'm going to illustrate different taxis using different colors. So, in this case, there is a yellow taxi and there is a purple taxi. And there are two kinds of data items generated by these taxis. The GPS events, which carry information about the location of the taxi, may be time-stamped, and these are denoted by rectangles. And then there are ride-completed events denoted by triangles, which carry information about fares when the customers finish rides, right? And so here is the computation. So in the first phase, maybe we want to compute the revenue for each taxi every hour. And to compute the revenue, you need to compute the distance traveled by the taxi and the fare generated by the taxi. So for the distance traveled, the temporal ordering of the GPS events is important because these would be time-stamped and they need to be processed in the order they are generated to compute the distance correctly. But to compute the fare, you can think of the ride completed events as a bag. So just a relational aggregation where you want to compute the total fare. Right? Having computed the total revenue generated in each hour, maybe you want to mark certain hours as peak hours, and this will, whether an hour is a peak hour or not, will depend on whether its revenue is much higher compared to the revenues of the adjacent hours. So I'm using this as a representative of computation that is time series dependent. So in many of these healthcare monitoring applications, you want to do time series dependent computations like smoothing and detecting surges and peaks. And this marking peak hours is representative of such sequential time series dependent computation. The third step of this computation is to designate certain taxis in an hour as high-performing taxis or star taxis, and these taxis could be the ones whose revenue is much higher in relative terms compared to the revenues of the other taxis, right? So this is a more classical relational computation. The exact definition of which taxi is considered a star taxi doesn't really matter, but this is something that's easy to write in a traditional query language like SQL. The time series dependent computation in the second step, that's the one that's not typically well supported in relational query languages. And finally, what we want to do is and that's the goal of the computation here, is to compute taxis which are star taxis during two successive peak hours, right? So this is kind of a joint, except it's a temporal joint. So for every peak hour, you have to look at the taxis that are star taxis in that hour and take a join by looking back into the past peak hour, right? So this kind of computation, which is a mix of sequential and relational computation and has somewhat complex synchronization requirements. So it's not just involving parallelization based on keys or relational aggregations, but certain things can be parallelized, but the sequential computation of, say, computing the distance traveled by a taxi, there the GPS events have to be processed in the temporal order. So there, they have to be so you need synchronization to enforce a consistent ordering of all the GPS events. So that type of computation is not well supported in the APIs of the stream processing systems that I listed a few minutes ago, right? So the user then is left with three unsatisfactory solutions. So all these systems allow the user to write low-level code. So you can always program whatever you want at the low level, but that's manual and error-prone. Or you can write some kind of a data flow model in a system like Flink and ask it to parallelize, but actually we have evidence to show that in fact in such settings the parallelization could be incorrect and the result of the computation could be non-deterministic, right? So you don't have guarantees of correctness in that setting. The other possibility is you set the parallelization level in these systems to be 1 and do everything sequentially when the result is then guaranteed to be correct. But then you are foregoing the opportunities for parallelization, and then the latency could increase, right? So so programmability in this context, when you have a mix of sequential and relational or time series dependent and more traditional relational computation, is what drives the work that we are doing. And if you think in terms of the theoretical foundations for models for streaming data, then actually there is very little work. So compared to, for example, the models for, say, relational computation, where there is a beautiful theory underlying relational query languages, and for sequential computations in themselves, there is a lot of work on transducers and automata and logics and understanding expressiveness. But when there is a mix, there is relatively little work. And if you look at the theoretical research in a conference like PODS on streaming computation, it's mostly based on algorithms, so which is streaming algorithms. So given for a specific computation, what's the best, what's the minimum number of resources that are needed in terms of, for example, the state that needs to be maintained to compute the answer in a streaming fashion, and can the answer be approximated? Is there a trade-off between accuracy and accuracy of the computation and the memory needed to compute, right? So much less in terms of models and logics, right? So that's the motivation for this talk. And what I'm going to do is propose a new model for streaming data. And this is the outline of my talk. So I will start by arguing that streams should be modeled as partially ordered multisets. And so these are called POM sets. But arbitrary POM sets are hard to compute with. So I'm going to propose a special kind of POM sets, a special class of POM sets, where the shape of this partially ordered structure will be specified using synchronization schemas. And that's the title of my talk. And synchronization schemas are types. And the series parallel streams, which are special kinds of POM sets, will be objects of these types. And then I'll tell you about a language for writing transformers over these series parallel streams with certain desirable properties. For example, they will express only deterministic and monotonic computations. Then I'll tell you a bit about the work, the ongoing work on defining a query language with these series parallel streams and series parallel stream transformers as the underlying foundation. And I'll conclude with an invitation for future research. So in fact, this is ongoing work, and there are many interesting open directions, and I'm hoping that I can get some of the PODS researchers interested in this thread, because I think there is a lot of interesting work that could be done in this space. So let me start by arguing that a good way to view streams is as partially ordered multisets or POM sets, right? So before we talk about POM sets, let's think about the more traditional model for formalizing streams, right? So the input stream can be viewed as a finite sequence of input items. And if the input items are of type A, and if the output type items are of type B, then we can think of the stream transformer as a function from A star to B star, sequences over A items to sequences over B items, right? And we would like this function to be monotonic. So throughout my talk, when I say monotonic, it's going to be monotonic with respect to prefix ordering. So if I extend the input stream with respect to the prefix ordering, we would like the output stream to be extended so that you are only adding items to the output stream, so that then such a computation can be implemented in a streamable fashion. It's going to be an incremental computation, right? So the basic abstraction here is that the stream is a linear, totally ordered sequence of items of a given data type, right? But this is overly restrictive for two reasons. One, from the query processing perspective, a sequential computation is hard to parallelize correctly. Whereas we know in advance that many queries have relational aspects. So for the query that I just described, there was like a join, or the total fare could be computed using relational aggregation, which is easy to parallelize. And there is a lot of beautiful theory and also practice on relational query optimization. So a purely sequential view would be foregoing something in terms of what we can do in terms of efficient implementation. From the perspective of data generation, we know that events in a distributed system are not all causally ordered. And there are protocols to enforce a logically consistent ordering across events of a distributed system. But to enforce such an ordering, you have to pay an overhead in terms of synchronization. And so if we start off with this basic assumption that the input stream is totally ordered, then we will be paying this overhead to begin with. And that's, again, the performance penalty that could potentially be avoided. At the other extreme, you could think of the input stream as, as a relation. Of course, it's arriving in a streaming fashion, so the relation is getting incrementally updated, and then the query itself could be a relational query. But this view, purely relational view, is not, in fact, it's not quite feasible in this context, even for a simple query which says that every minute output something which is some relational statistics of all the events that you have seen in last 1 hour, which is a traditional standard sliding window kind of computation. Adding these markers, say, which mark the passage of 1 minute, is crucial, because these markers allow you to focus the relation to only, a temporally finite history, so that the relation doesn't keep growing in an unbounded fashion, and the state can be flushed once in a while. Also, when you have relational aggregates, at these markers, which are temporally, the temporal ordering of these markers is important. That's when you produce outputs. So to produce outputs and to flush the state, we need some kind of temporal markers. And so a purely relational view is not quite feasible, but one view that has been very popular in streaming database literature is to view the input stream as a sequence of relations. So maybe the input is partitioned into windows, and within each window we have a relation of events, right? Yeah, and there are different versions of windows, but that's the basic idea. So this actually goes back to work by Widom and her group in the early 2000s, and they defined something called a continuous query language, which is an extension of SQL. And there has been a lot of great work by Meyer and his colleagues on formalizing this idea of punctuation markers, giving a good formal semantics to relations with these temporal markers, right? But if you think about streams that are partitioned by keys, then that's not a sequence of relations, and it's a different object. So actually, if you look at these streaming extensions of SQL, there is kind of a mismatch between different kinds of objects, right? So at some points it's sequence of relations, and then there is partitioning, but then you can't nest them. And this is because of type mismatch. So different objects have different types. So there is a solution to this, and which is related to partial orders. And so let me illustrate this by going back to the query that I described at the beginning. So again, we have these taxes generating some GPS events and some write completed events. And the first step of our computation was to compute the revenue of each taxi every hour. And this involved using the GPS events, where the order of the GPS events of the same taxi was important, to compute the total distance traveled by the taxi. So that's a sequential computation. And then using write completed events, which carry information about, when a customer finishes a ride, the fare paid by the customer. So you just apply a relational aggregate to compute the total fare charged by the taxi. And then once you know the distance traveled and the fare charged, you can compute the revenue, right? So if we forget the exact computation that's corresponding to this query, but focus on which orderings between different data items are important to compute this answer, we get this partially ordered structure. First, since we want to compute something every hour, we need to introduce these synchronization markers or temporal markers corresponding to end of hour events. And they are depicted as these stars in this picture. And in between two star events, which are these end of hour markers, I have GPS events of different taxis, where the events of yellow taxi are totally ordered. The events of purple taxi, GPS events of the purple taxi are totally ordered. But the relative ordering of the events between yellow and purple taxi is not important. Furthermore, the write completed events can be just viewed as a batch. So there is, I don't need any ordering of the write completed events even of the same taxi for the purpose of this computation, right? So this, now I can think of this partial order as my logical view of the temporal ordering of the events in my stream. And it just captures this constraint that the GPS events of the same taxi are linearly ordered, and all events are ordered with respect to this end of hour synchronization markers, right? And then these constraints then can be viewed as a contract between the implementation and the query processor, right? So what's this contract reflecting? Well, from the perspective of the data generator or the implementation, the events that are ordered, right? So the implementation should somehow enforce a strict temporal ordering between those ordered items, even if they're generated at different nodes of a distributed system. So those are the events for which the implementation is expected to pay the synchronization overhead and enforce some consistent temporal ordering. For the unordered items, the implementation doesn't need to enforce any synchronization, but then the burden is on the query processor that if these events are viewed as temporally independent, order independent, then the result of the computation should not depend on the order in which they actually get delivered. And in fact, they could be processed in parallel, right? So there is also an opportunity for parallel processing of unordered events, right? And if you think about this structure, it's the correct mathematical formalization of this is as a partially ordered multiset. So you can think of this as a graph where the vertices are labeled with tuples or data items, and the edges correspond to the order, right? And the structure is partially ordered. It's a multiset because multiple vertices could be labeled with the same tuple, right? So this is just like the distinction between relations and backs, right? So these POM sets are, they have a nice mathematical structure, and they were first considered in the context of concurrency theory in the 80s by folks like Pratt and Mazurkiewicz. And the motivation for them was to capture true concurrency semantics. And this was just, how to model executions of a distributed system. We are going to go a step further. And well, firstly, our application is a bit different. We are going to use POM sets to model the data that's being generated. And we want to focus on transformations over these POM sets so that our queries will be transforming POM sets to POM sets, right? And sequences, bags, sequences of relations, sequences partitioned by key values, these are all instances of POM sets, right? So, and since everything is a POM set, you could nest them arbitrarily, and you get, so nested windows and all kinds of objects that have been considered in streaming database literature can be formalized nicely, right? And both bags and sequences are special cases. So the theory of relational and sequential transformations can be a starting point, and those could be the building blocks for transformations over POM sets.
Rajiv, there was a question, and the question comes from Pablo, and says, is this a serious parallel graph, or there can be some interaction between branches?
A good question. So yeah, I'll come to it in a minute. In fact, yeah, so I'm going to answer this. It is a series parallel graph, and we are going to impose a structure on POM sets. So we don't want to deal with arbitrary POM sets. And that's and why is that? So there are challenges for computing with POM sets. So in fact, there is no well-developed theory of computing with POM sets or transforming with POM sets, because it's a much more complex structure. So the first question is, how do we specify the desired ordering constraints? And the second question is, how do you specify stream transformations? So we would like a stream transformation to be monotonic, or we would like the transformation to be, we want to make sure it's consistent. That means the result of the computation is not dependent on the order in which items that are viewed as logically unordered get processed, right? And so to do this for arbitrary POM sets turns out to be challenging. So what I'm going to propose is actually synchronization schemas is a way of these are types that specify POM sets of a certain kind. And those objects of this type are going to be series parallel graphs. But this may be, so maybe this is a good time to take a little pause and see if anyone else has questions.
There are no other raised hands at the moment. So please go ahead.
Okay, thanks. So before I tell you about synchronization schemas, it builds on relational schemas. So what's a relational schema? Well, in the database community, everyone knows what they are. I'm going to use them in a particular way. So let me define a few things. So the idea of a relational schema is to define the structure of data, and maybe in conjunction with some integrity constraints. For the purpose of this talk, integrity constraints are not relevant, though they can be added, but for simplicity, we are not looking at them at this point. So going back to our example, we could say, the data consists of 3 different kinds of tuples: end of R tuples, which carry, say, date and R, GPS tuples, which carry maybe location and taxi ID, and ride completed tuples, which consists of, say, taxi ID, ride ID, and cost, right? So the relational schema then is given by listing the names of relations for every relation, what are the fields and what are their types, right? So I'm going to call the names of these relations, such as end of R, GPS, and ride completed, as headers. And the keys are field names. So for example, taxi ID could be a key. And then the tuples, these are going to be the data items in the streaming world, and these are these are standard entries in, in relational data. So the idea of a relational schema was to express some structure of the data, and then you could say that, okay, take a join between GPS and write completed on the field taxi ID, right? So synchronization schema also expresses, builds on this relational schema, and it adds some temporal ordering constraints. So I may want to add a constraint saying that the GPS events and write completed events are independent, or GPS events are all linearly ordered, right? And so these constraints will refer to the headers, that's the names of relations, and maybe also to the names of the fields, right? And so this schema, you should think of this as a type. So those of you who are familiar with types, this whole framework has a very strong type theoretic foundation. And so in this setting, I'm thinking of them as types. And these types will specify the shapes of the partially ordered streams. And the series parallel stream will be an object of this type. And the schema is going to be defined inductively. And here are the clauses. And we will go through these one by one in the next few slides. But just a preview. So a schema could be a bag of tuples, could be a sequence of tuples. It could be a parallel composition of two schemas. It could be a schema partitioned by some key values, or it could be a schema synchronized with some synchronization markers. So let's start with our base schema, bag of H. So H is a list of headers, or list of relation names, and an object of this type is an ordered collection of tuples of type H. So for example, if the schema was bag of write completed, then a series parallel stream of this type is just and completely unordered bag of write completed tuples, right? The other base schema is sequence of H tuples. So it just so bag of H means completely unordered collection of H tuples. Sequence of H is a totally ordered or linearly ordered sequence of tuples of type H, right? So if I say sequence of GPS, an object of this type would be a linearly ordered sequence of GPS tuples, right? As it turns out, technically this operator is definable using other operators. So these base schemas can be combined to generate series parallel streams with more complex shapes using 3 constructs. So one of them is key-based partitioning, right? So if K is a set of key names and S is a schema, then partition by K comma S is a complex schema, and objects of this type is a set of parallel streams, each of type S, which is indexed by the values for the key fields in K. And so going back to our example, so sequence of GPS says, it's a sequence of GPS events. If I partition it by the taxi ID field, what I get is a set of GPS sequences, one for each taxi ID, right? So there could be a sequence of GPS events from the yellow taxi and a sequence of GPS events from the purple taxi, right? So it's an index set. So it's like unbounded, unordered parallelism. So if you look at the type of this sequence of GPS events of the yellow taxi, what is its type? So of course it's sequence of GPS events, but it's more refined than that, because these are all the GPS events for which the taxi ID field is yellow, right? So in standard type theoretic terms, this is a refinement type, right? So the refinement type is, so that the type of this object is sequence of GPS, where with the additional constraint that the taxi ID is yellow. The second construct to build more complex schemas is a parallel composition, and syntactically we call it a par of S comma S prime. And an object of this type, well, you can think of these as graphs. So it just two disjoint graphs. So one of type S and one of type S prime, and it's there are no edges going between them. It's required that the names of headers that appear in S are disjoint from names of headers that appear in S prime. So this is important because if I gave you a linearization of this partially ordered structure, and if I gave you a schema, one can uniquely reconstruct the partial order. And so that, and also while processing, if you are processing an input stream, and if the schema says parallel of S comma S prime, you can, based on the type of the tuple, you know that it either belongs to S or it belongs to S prime, right? So in our example, if I have, so the bottom circle shows a bag of write completed events. The top is a GPS events partitioned by the taxi ID. If I compose them using the parallel operator, then I get the structure, which is combination of the two. And the type of this is the schema part of the two schemas that we already discussed. And the final construct is hierarchical composition, which is we denoted by sync of H comma S. So H are the synchronization markers. So in our example, these would be the end of R markers. And so if S is an existing schema, which could specify streams of some complex type, then sync of H comma S specifies streams which is a linear sequence of events where the H, the events of type H act as synchronization markers. And in between these synchronization markers, you have objects of type S, right? So you have a linear sequence of events of type H interspersed with substreams of type S, right? And what this is expressing is that, when an event of type H happens, this is a punctuation or a synchronization marker. But so this is actually a generalization of, say, the sequence of relation view, or or the temporal windows or event-based windows, because in between these markers you can have more complex streams, right? Yeah. So going back to our example, the synchronization marker was end of R, and then in between them we have a parallel composition of two objects. So one is a bag and one is an index set, right? And this is exactly the structure that we wanted to express for our query. But now the difference is that it is a POM set, but it's a POM set of a very particular kind, which is built using these, a small set of inductively defined constructs, right? So to recap, a schema, a synchronization schema is a type that captures the shape of partially ordered streams. Its definition is inductive. It extends a relational schema. And as I mentioned, sequence of H is actually can be defined using other operators. So it's either a bag, a parallel composition, an index set, or a hierarchical structure that introduces synchronization, right? And the series parallel streams are inductively defined objects. So this actually gives the structure, and in fact, this inductive definition will help us to define computation over these objects, right? These do not capture all POM sets. And in fact, yesterday, there was a question about what kinds of partially ordered structures that cannot be captured by these. So actually, so one example is, suppose I have 4 types, say A, B, C, D, and imagine a partial order, which is kind of think of a square where the vertices are labeled A, B, C, D, right? So A is dependent on B and D, and D is dependent on A and C, and so on, right? So this is not an example of a series parallel graph. And this cannot be defined using this inductive definition, right? So why do we want to restrict ourselves? Well, this is still general enough to capture objects that arise that we have looked at in typical streaming computations in our examples, like sequences and bags and sequences of bags and so on. But the inductive definition is actually, that's what helps us to compute with this class of POM sets, right? And that it suggests an inductive definition. But the series parallel streams have a nice structure, and you can define operations just like you define operations on sequences and relations and trees. You can define operations on these objects. For example, prefix, which would be useful in defining monotonicity of computation. So if you look at the series parallel stream on the right, and it's a partially ordered structure, if you take a cut through this partially ordered structure, what's to the left is it's a potential prefix of the series parallel stream, and you can define concatenation, and you can define operations like that, right? If you look, the series parallel streams can also be defined as what's in the literature called as a Mazurkiewicz trace by the set of all its linearization. So that's a different representation of the partial orders. So in this visualization, what you see is a series parallel stream on the right, and one possible linearization which basically retains all the items of the series parallel stream, but they're linearly ordered in a way that's consistent with the partial order, and that's a flattening or a linearization. And the theorem that we have is, if I give you a linearization, and if I tell you the schema, then you can uniquely reconstruct the series parallel stream. Right? So this is not possible for general partial orders, but here the synchronization schema actually carries enough information to tell you which items are logically ordered and which are not, right? So this is important again for for correct parallelization. And a final bit about these structures is that you can define a nice you can define subtypes over these schemas, right? So actually, it's easier to explain this using an illustration. So suppose, so this is the series parallel stream we have been looking at, right? And in this case, between every end of our event, the GPS events of the same taxi are ordered. And if I drop those ordering constraints, then I get a structure which now we see on the right, where in between two end of our events, everything is a bag. There is no relative ordering of any of the events that happen within an hour. So the GPS events and the write completed events are all unordered. So the type of the structure on the right is expressed by the schema, which is where end of R acts as a synchronization marker, and what we have in between is a bag of GPS and write completed events, right? And so this schema is a relaxation of the schema on the top, right? Which is expressing more ordering constraints. So in type theoretic terms, it's actually, the schema on the bottom is a subtype of the schema on the top. Every object of one type can be interpreted, every object of the top type can be interpreted as an object of the bottom type, right? So given two schemas, one may ask, can you check whether one schema is a relaxation of another one? And that's possible, and in fact, it can be done in polynomial time. There is a relatively easy algorithm to do that. So next, I'm going to tell you about transformers over these objects, but this would also be a good time to take a little pause and see if anyone has questions.
There are none at the moment.
Well, it says two participants raised hands, so yeah.
Oh, I don't see any. Maybe that's, do we see them? Because it does not show me it. Okay, it's, that's a question to the organizer. I don't seem to. I mean, may I ask the participants to please type your questions during the talk in Q&A? Okay. Finally, I am. Okay. Dan, you should be able to talk and ask a question.
Yes. Okay. Can you hear me?
Yes.
Okay. So a quick question. So you showed us a prefix, but the schema that you, the data that you represented as a prefix didn't seem to have a schema. So are your well-typed data elements or data sets, are they closed under schemas? Yeah, the prefix on the left. That was my question. Thanks.
The schema for the prefix is exactly the same. So the prefix ordering is for data items of the same schema, or there is subtyping also.
Got it. Thank you.
Okay, and okay, Jan, you should be able to ask a question.
No. Hello, can you hear me?
Yes.
Okay, thank you. Yeah, just a detailed question, but I'll ask it nevertheless. In the partition by K, S construction, is there any relationship between these keys on the one hand and the headers that appear in this complex schema S on the other hand?
Yes, the keys should appear in all the headers that are in S. But alternatively, you could just think of it as a no-op. If those keys don't appear, then it also could be interpreted as missing fields. But it's easier to think if every key that appears in K is a field of every relation name that appears in S.
Yes, okay, thank you, that's clear. And just a small quick other question about the unique parsability. So if I have just a sequence of tuples, it probably is also possible that there is no schema for that sequence.
No. So I think, no, the parsing could be different based on the schema. So you have to give me the schema. So if you give me, so if I give you a sequence of tuples over, where if the set of headers is S, if the set of headers is H, and if the schema involves all the headers in H, then given any linear sequence of H tuples and the schema, there is a unique parsing. If I change the schema, then then the parsing will change. But yeah, it always exists here.
Very interesting. Thank you.
Okay, and we have a question from Wim. Wim, go ahead. You should be able to talk.
Sorry, I didn't think I raised my I raised my hand, but I can ask a question nevertheless. I was wondering if, as far as you can see, these series parallel representation that you use, does this really cover everything that you have seen in the wild, or are there things around that that you think are not captured here?
Yeah, that's. I think in terms of the examples we have looked at, yeah, we are able to model everything. Yeah. So in terms of what logical structure they represent, right? So they're capturing which ordering requirements are important and which are not. And so there is a precise characterization of which partial orders can be represented by series parallel graphs, and the ones that are excluded don't, those the corresponding ordering constraints don't seem to appear in the queries we have looked at. Yeah.
Okay, and does the connection between series parallel and low tree width play a role somewhere in nice complexity results, or?
So that's a good question. So in fact, we don't have, this is just ongoing work, and it's actually an invitation to, folks like you who know about these complexity results. So one complication here is that we have this key-based partitioning, which seems crucial in all the practical queries, and hence so it's not so the theoretical results, there seems to be a gap, and I'll come to this at the end of my talk, but yeah, so the short answer is we don't know. Yeah.
Okay, thank you.
Yeah.
Okay, Rajiv, there was one question typed on the questions on the Q&A board, and I would suggest you take that, and after that we'll proceed with the talk because there will be an opportunity to ask questions later. And the question asked is from Ming Chuan Wu and says, in the relaxed schema example, the schema did not specify partitioning. However, the illustration shows partitioning on taxi ID. Why is that?
No, so the relaxed schema doesn't do partitioning, right? Yeah. So I'm not sure how to interpret your question, but in the relaxed schema, I don't want partitioning. By the way, if I were to view this bag as partitioned by on the taxi ID field, and the partition thing also is a bag, then those are actually equivalent schemas. So let me simplify it. A bag of GPS and partitioned by taxi ID bag of GPS. These are two, as partially ordered structures that they specify identical things, though the schemas are different. And if you are expressing the computation by structural induction on the schema, they would be structured a bit differently because one would actually let you do key by partitioning, but the objects they are processing are of the same type. And so these two are equivalent types. As the set of objects they represent, they are the same types. And type equivalence is also decidable in p-time, right? But so when there are sequences, the partitioning by is crucial. But if it's bags, then partition by is kind of it's an option. It could be viewed as redundant because it's not adding any. There were no ordering constraints, and it's not adding any new constraints or relaxing constraints. I hope that answers your question.
Okay, I suggest we go ahead with the talk, and for everyone, there will be an opportunity to ask questions at the end of the talk as well.
Okay, thanks. Yeah, but thank you for all these questions. And what I want to do in the next 10 minutes is to tell you about, give you a hint on how you would go about defining transformations over these series parallel streams. And I think technically this is the most interesting part, but I'm going to just give you a flavor of what issues arise, because I think going through the technical details may be too much in this virtual setting, right? So what is it that we want to specify, right? So you have a transformer, and suppose I tell you the input schema, right? So, and then I tell you the output schema, then this transformer should specify a function from streams of the input schema to streams of the output schema, right? And what's the motivation for theory of transformers? Well, these can serve as an intermediate representation between the user queries. So the user presumably wants to think in terms of more traditional operators like joins and filters and maps, and maybe some things which are more specialized to the temporal aspect, like time series dependent computations. But if we transform them to these transformers, then we can think of query optimization and also expressiveness and evaluation complexity in this world of transformers. And I have worked a lot on transducers, so I was naturally interested in how to define transducers over these structures, right? So the specific object that we want to define, we are going to call series parallel stream transformer, or SPST. And it in a streaming fashion, it maps an input SPS to an output SPS. It's convenient for these transformers also to take an initial value and return a final value. And this would be useful when these transformers get called by higher level transformers, right? And the final value, for example, is useful to do, say, aggregates, like relational aggregates. So when a synchronization marker arrives, you return the aggregate of the computation you have done so far, right? And we are going to define these transformers by exploiting the structure of the input synchronization schema. And this is where the types come in to play and help us a lot, right? If you're thinking about arbitrary partial orders, then defining this transformer would be very low level. You would have to keep track of kind of the frontier of the partial order, and it just turns out to be messy. But now it can be defined more modularly or inductively, right? And we would like a formal semantics as a deterministic function from these input streams to output streams, right? So let's start with the case of relational SPST, right? And so the input then is maybe a bag of H tuples, the output could be a bag of H prime tuples, and all we would, so this can be written in your favorite relational language. We just want to make sure that if you produce some outputs, you don't retract them. So that's what we mean by monotonicity here, is that if input bag extends, the output bag will only extend, right? And the final value could be useful for computing the relational aggregate, right? So let's look at the case of parallelism, right? So suppose my input schema says it's a parallel composition of S1 and S2. So in that case, my input stream is a parallel composition of two graphs, I1 of type S1 and I2 of type S2. And what we would like is that this transformer should exploit this parallelism so that, in the actual implementation, I can then, I know that the items belonging to S1 and items belong to S2 can be processed independently or in parallel, and that will allow us a safe parallelization. Also, if I have defined a transformer over inputs of type S1, I should be able to reuse its definition to define the transformer T. So that's kind of modularity, right? So I've defined some transformations over S1, substreams of type S1. I should be able to reuse that computation. So I'm skipping some technical details, but informally, this is what this transformer looks like. So suppose T1 maps streams of type S1 to S1 prime, and T2 maps streams of type S2 to streams of type S2 prime. Then I can define a transformer which just runs these two in parallel and map streams of type S1 parallel S2 to streams of type S1 prime parallel S2 prime. So there are initial final values, and those could be handled in a natural way. For example, the final results of T1 and T2 could be combined to produce the final result of this composite transformer, right? So in this illustration, it seems like the S1 prime and S2 prime are disjoint. They can't have common tuples. So the natural question is, can there be headers that are common to both S1 prime and S2 prime? Or more generally, is the shape of the output stream, does it have to be isomorphic to the shape of the input stream? And so the answer is no. Some relaxation of this thing are possible. And so there should be some kind of a bisimulation-like relationship between the shapes, which is which takes care of the ordering dependencies. So basically what you want is that events that are unordered in the input stream should not produce events that are ordered in the output stream, right? And so this constraint can be captured more abstractly, but the details are in the paper, and the same ideas can be extended to handle the key-based partitioning case, which can be viewed as a generalization of MapReduce, right? So the main thing that happens in key-based partitioning is that you start a thread of the inside transducer for every new key, and when you return, all these threads finish their computation, and then you can reduce their results, producing a number of new output tuples. But it's basically a case of unbounded index parallelism, which generalizes this parallelism of the bounded parallelism that we see in this example. But I want to highlight some interesting aspects about the hierarchical case. And this is where I think some perspective from programming language semantics and types is actually quite useful. And even this can provide some insights into the work that has been done in defining semantics of punctuations and end of stream markers in the relational streaming database folder. So suppose the input schema is of the type sync h comma s prime. So this is specifying an input stream where events of type h act as synchronization markers, and in between we have streams of type s prime. And if I have defined a transformer over streams of s prime, I should be able to reuse it to define a transformer to process streams of this more complex stream, right? And the definition of this hierarchical transformer should be intuitively, it should maintain its own state, which gets updated when you process h tuples. And whenever a substream of type s prime starts, it calls this transformer t prime. And when it sees the next synchronization marker, the t prime returns. And then that return value then can also be used to update the state of it. So so that would be the natural definition, right? So one semantic complication that arises is, so suppose we want to define formal semantics for t prime as say a function from input streams to output streams, right? So if you think about this, so imagine you are processing the input stream I1, which is of type s prime. Well, if the next item that comes, if it belongs to one of the relation names in s prime, then that item is actually part of I1. And at that point, t prime should not return. But if the next item happens to be the synchronization marker, then the transformer t prime should return. Now, while it's returning, it does some extra computation. But think of the case when in key-based partitioning, s prime may be running, t prime may be running many subthreads, and then they may all end, and then you may produce a lot of additional output tuples, right? So the semantics of t prime should include that possibility that what happens when it returns, right? And also should allow for the possibility when it continues the computation. And this is exactly the the challenge that shows up in defining semantics of punctuation markers, or handling the end of stream marker, where in advance you don't know whether the end of stream is coming or not, right? And I think we have a nice clean solution where we define two semantics. One, which we call open semantics, which is assuming that the transducer will continue to compute, assuming that the next item will be part of the current stream, and it maps initial value and input stream to an output stream. And the closed semantics, which assumes that the transformer will return, and it maps initial value and input stream to a final value, and the output stream, which includes all the additional output tuples that you may be forced to generate when you are returning. Again, I'm differing the technical definitions and details to the paper, but I want to summarize some of the results about these transformers. Firstly, it has a deterministic semantics. So it defines a function over series parallel streams so that this non-determinism because of ordering kind of goes away. It allows safe and flexible parallelization. So it's safe. So things that are handled in parallel, they are handled correctly. And the patterns of parallelization that it can handle are more than what current APIs for stream processing systems allow. So it's more than this key-based partitioning or relational aggregation. So in fact, this the degree of parallelization changes with the stream, and it's more temporally varying and data-driven. So formally, the open semantics is monotonic. So the precise theorem is that for all initial values x and for all input streams I and I prime, if I is a prefix of I prime, where the notion of prefix is over these series parallel streams, then the output stream on I is a prefix of the output stream on I prime, right? And this means that the computation can be implemented in an incremental fashion. it's modular. So if the schema S involves subschemas S prime, then the transformer T over S can be defined using the transformer T prime over schema S prime. And moreover, the semantics of T can actually be defined using the closed semantics of T prime. And finally, these transformers are composable, right? That I can construct a pipeline, say T composed with T prime, and the requirement here is that the input type of T prime should be a relaxation of the output type of T. So this is really like functional composition, because this relaxation is just subtyping. So what T produces, so T prime should be able to consume. It doesn't have to be of the same type, right? But has, so the subtyping relation should hold, right? So at a higher level, instead of structuring the computation as a data flow graph, where the parallelism in the data flow graph exposes some parallelism, now you can express it as a sequential pipeline, because the types themselves capture the parallelization, and then more flexible forms of parallelization are expressible than what's possible in just duplicating nodes in a data flow graph. So this may also be a good time to check if there are more questions.
I do not see any at the moment, so please go ahead.
Okay, thanks. So I'm going to spend next 5 minutes to tell you about high-level query languages, and this is more like work in progress. So so the vision here is that one would come up with a nice library of high-level queries. So for example, in the relational world, we know that filters, map, join, union, these are like core operators, and and those we have a good understanding of operators in the relational world. So what are the operators that the user can understand in this world of series parallel streams? So that's so we have some ideas, but no definitive answers. But the proposed architecture is that once you come up with this library, you can map it into the query compiler will map it into a pipeline of these transformers, and then those an optimizer could map it to a distributed implementation, right? So here is a list of queries that we have defined, so filter, map, a variety of windowing constructs, relational and sequential aggregations, event marking using regular expressions in the style of complex event processing, different kinds of joins, map reduce. There are new opportunities, so there is an operator called lift. So if I have defined a query over a schema S, I can lift it to a query over schema S prime, where S is a subschema of S prime. And so there, there are ideas using polymorphic types and higher order types. And instead of going through this list, I'm just going to give you a flavor by going back to the example that we started with, and that should give you some idea of what these queries could look like. So the computation that I described at the beginning of this talk was, you have GPS events that carry some information about locations of taxis, and write completed events that carry information about fares of tax collected by taxis. And what we wanted to do was to compute the revenue of each taxi each hour, mark certain hours as peak hours, mark certain taxis as star taxis in each hour because they're high-performing taxis, and then output the taxis that are star taxis during 2 successive peak hours. Right? So the first stage of this computation involves 3 sub-computations. So one is within each hour, compute for each taxi the total distance traveled each hour using GPS events, right? And this is sequential aggregation, and we can actually, this is like a list iterator, right? Which is just iterating through the GPS events of a taxi, and we can write this as a list iterator, and this would be a sequential aggregator with, the aggregation function initial value would be, that's like one of the queries that we allow, right? If I want to compute the revenue of each taxi, it's just a relational aggregation over the right completed events. So this could be written in SQL or, any relational language, right? And then once you know the total distance and the fare, you can just compute the revenue for the taxi, right? And so you can transform the data of each taxi in each R by the revenue tuple, and then the input stream will be transformed into an output stream, where the type of that output stream still has a end of R as synchronization markers, but in between it has a bag of revenue events, one for each taxi. The next step of this query was detecting PCARs, which is an example of a time series dependent computation, right? So this is the input stream where now, we see multiple taxis with different colors. And now what we want to do is to compute the first part of this query is for each R, I want to compute the total revenue. And so this total revenue can be added as a field to the end of R tuples, right? So I can just do a relational aggregation of all the revenues and say that 538 is the total revenue at the end of the, in the second end of R tuple, right? So this is relational aggregation, but using a specialized operator, we could add this as a field to the synchronization events, right? And then what we want to do is to mark some of the tuples as PCARs, right? So the so for simplicity, let's assume that the hour with revenue 538 is a PCAR because its previous hour had less revenue and the next hour also had less revenue, right? So how do we compute this in a streaming fashion, right? Well, firstly, what do we want to output? Well, we want to add a bit or a mark to the end of our tuples. So in the output stream, now some of the end of our tuples are denoted as, they're marked using red color because those are the PCARs. So this would be like adding a Boolean field to the end of our tuples. And in the streaming fashion, so when we see the value 538, we cannot determine that this is a PCAR because we have to wait till we see the value 420 of the next R before we can declare 538 to be the PCAR, right? So this is what happens when you want to detect peaks and surges and things of that nature. But so when you see 538, before you see 420, you see all the revenue tuples of the next R. So those have to be stored, and we have to delay the producing that output before we can output the 538 tuple tag with the red bit, right? So this this peak is, but now can be defined as a base query, and one can start thinking about what's the best streaming implementation of something like this. The third step of this computation is filter only star taxis. So for each R, you look at the revenues of all the taxis, and you want to declare some of the taxis to be star taxis and filter out the rest. And this is a purely relational query. And what it means for a taxi to be star is it's not crucial for this example, but whatever the definition is, maybe it says that in the first R, the purple taxi and the orange taxi are star taxis. In the next R, maybe the yellow taxi is the star taxi, right? So now that this is how our stream looks like. And then the final stage of the computation involves some form of a temporal join. So maybe in the hour which is marked 1005, that's a PCAR. The star taxis during the past hour were the purple and the green one. And you have to look back to find the previous peak, which was 538, and look at the bag of star taxis and then do a join, right? And this is a self-join on the taxi ID field. And this is an example of, temporal join. And so, in some temporal databases, these kinds of operations are studied, but now we can specify them using regular expressions where the atoms are predicates over the tuples, right? So how far back do you look in time? Well, that can be specified as using a regular expression. So the precise definition of the this is an example of a query that we have is in general, if I have H1 as this synchronization markers, and in between H1 tuples, if I have bags of H2, then I can say that do the join of H2 bags on the field F, where you are looking at the history, the temporal ordering of H1 fields, and how far you have to look back in the past. It's specified by a regular expression R, which is over the fields of the H1 tuples. So the specific definition here is a bit technical, and I don't want to describe it in the talk, but the reason I wanted to mention this is that once you define this kind of operator, you can give a bound on how much memory would be needed for streaming evaluation. And it turns out that you would have to remember as many bags as the size of the regular expression R. So this is the kind of query which, it would be hard to specify using existing APIs. Particularly, you won't be able to do a good optimization. But so marrying this world of relational world with these regular expressions and the sequential computation related constructs can lead to interesting results, right? So to summarize this SPS queries, so it's work in progress, but what we have is a list of some transformations, which for now does not have any good theoretical basis in terms of why we chose these constructs, but these are the constructs which seem useful to specify some existing queries. You can specify both relational and time series dependent operations, and queries can be nested, applied to substreams, so they're nicely composable. And the key to compositionality is that every object in our world is this series parallel stream whose type is specified using a synchronization schema, and only checking subtypes is lets you specify which queries can be composed, right? And this, and then you can map it to a parallel implementation pretty nicely. So I'm going to wrap up in next 5 minutes, and then we can move on to questions. So this is more like the directions for future research and more of an invitation, particularly to the the folks in PODS community who have a lot of expertise in studying logics and transducers and defining queries over data models. So the first thing that we want to do is to show that this parallelization, safe parallelization in practice has some benefits, right? So we do have some ideas of how a pipeline of SPSTs can be optimized to map to distributed implementation. And the benefit would be that compared to existing systems, that the parallel implementation would be provably correct. And there are also opportunities for distributing state to minimize communication. For example, since we know that in going back to our example, the GPS events of the same taxi could be processed in parallel. And if the GPS events of yellow taxi and the purple taxi were being generated at 2 different nodes, we could push the state of the computation to these taxis themselves, right? So this is the idea of edge computing, and in general, how to distribute state from from a globally specified computation is hard, but here the structure of the query could help us with that. And we do have some results, and there is a paper in PLDI 2019, and there is a paper currently under submission where we show that some of these ideas can give you better performance compared to Flink and Spark. The second thread of research is really about theoretical foundations. And if you stare at this structure of the series parallel stream, you see relations, you see sequences or strings, the parallelism is like binary trees, which are ordered siblings. The key-based partitioning is unordered, unbounded trees. And of course, there is data. And there is also work on, say, data transducers and data logics in the PODS community, right? So this series parallel streams, because of their inductive definition, I think are a rich and clean mathematical object, which are worthy of study. But how to marry the relational world with the sequential world is not quite clear. And I'm hoping that people will look at these and come up with interesting results in terms of logics in automata and transducers. There could be opportunities for finding decidable fragments of queries, and also getting a good understanding of streaming query evaluation. But I want to mention that here it would be good to look at parallel complexity of queries, right, instead of just sequential complexity, because there is a natural parallelism in the objects that we are manipulating. So it's a bit different from trees, actually, because it's there is the parallelism. The parallel children here are really the ones that can be processed in parallel before the next synchronization marker arrives. Thirdly, there are opportunities for query optimization. So both the theory and practice of relational query optimization has had great impact. And now we have a mix of these temporal and relational queries, right? And just to give you a flavor of what's possible, so going back to our computation, in the first phase, we computed the revenue. In the second phase, we marked peak hours. In the third phase, we computed star taxis. If I swap the order of Q2 and Q3, if I first compute the star taxi and then mark peak hours, the semantics of query would not change. But then computing peak hours could be done more efficiently, because as I explained, to compute peak hours, we need to remember the revenue tuples of the subsequent hour before we can output this tuple, whether it's an hour, or whether it's a peak hour or not, right? But the amount of information that you have to remember will decrease if we have done a filtering in advance and only retain the star tax. Right? So how to do this automatically? What are the query rewriting rules which will let us do in a more systematic and automated way? It's an opportunity for future research. And finally, the reason I got interested in this space is from the perspective of formal verification. So in the distributed systems, now there is this hope that we can actually build fully verified systems, right? So what about fully verified stream processing systems, which are, I think, relatively specialized kinds of distributed systems? And there is a lot of work on how to verify synchronization protocols or fault tolerance protocols. But in this setting, if I want to say that, is the query being parallelized correctly or not, right? And actually, that's how I started thinking about these problems. And we realized that, for systems like Flink and Spark, there is no good, in fact, people haven't really looked at how to verify these systems. If I set the parallelization level to something, is the system doing correct parallelization? And so I think these synchronization schemas can actually form a basis for correct synchronization. But more in the short term, we can develop tools for rigorous testing and debugging. And one work that we have in this space is a tool called diffstream, which is a testing tool for differential output testing of Flink programs. And this appeared in last year's OOPSLA. And there is a lot of opportunity for researchers in programming languages and formal methods to look at this space. So to conclude, I have proposed a new foundation for computing with data streams, which is a special kind of partially ordered multisets, where the shape is specified using synchronization schemas. The objects are series parallel streams, and there is a definition of SPS transformers which exploits this parallelism and lets you define transformations which combine relational and time series dependent operations. It has a rigorous semantics which captures deterministic behavior, which is monotonic with respect to prefix ordering over input streams, and you can compose them in any way you want, right? And I have discussed some opportunities for both theoretical and practical research. So thank you for listening to me, and now we can switch to a more open Q&A.
Well, thank you very much, Rajiv, for this very interesting talk and opening lots of new directions, hopefully for our community. There is already one question, so I'll attempt to allow the Mia Moharana who asked it to talk. Yeah, you should be able to ask the question.
Hey, this is a nice talk. Thank you very much. I have four questions. Suppose whenever in streams you are looking for a trend, suppose say that, okay, I see continuously degradation of my resources possibly for continuously 5 minutes. In the use cases that it is very difficult to define a marker. So the pattern can stretch across any point of time and it can start anywhere. How to handle those type of situations with the schema?
Apologies, but I think there was a lot of static noise in the background, so I couldn't really hear what you were saying.
I couldn't hear there was lots of noise. So let me just read because the question was actually typed on the Q&A. So let me read this question from Q&A. And it says, how it enables searching patterns. Here it is difficult to define the marker and apply a schema.
Hello.
And that's probably, yeah.
Yeah, so I think I get the gist of your question, which is how do we introduce markers, right? So I think the way to think about this is maybe I have an input stream and I have one stage of query processing which introduces markers into the stream, and those could be based, these could be based on event processing. So for example, I could be processing a time series data, and I could say that mark the peaks, right? And this would be then those markers would be introduced at the right points, and this would be a complex sequential computation, right? And then downstream, the input stream will have these markers, and the downstream operator could have been predefined, and which says that once the stream has these markers introduced, this is how you compute. And there could be a lot of opportunities for parallelization, right? And then the query optimization question would be, can you combine these two phases so that while you are introducing markers, you can execute some of the downstream computation, right? But I think the idea here is to separate the specification, which now has precise semantics. So I think there is in the practice of stream processing, there is a lot of work on complicated forms of markers and windowing constructs and so on. But the semantic foundations are a bit shaky because the objects are not precisely defined, and hence I think there is no good basis for doing provably correct optimizations and provably correct parallelization and verification, right? Yeah, but all the ideas in that in the existing system C work on introducing markers in a dynamic fashion and processing complex forms of windows in a sliding fashion, for example, I think those we can build on that, right? Yeah.
Okay, thanks. So I am letting, I'm letting Angela ask a question. Angela, you should be able to speak now.
Yes, thank you. Thank you very much for your talk. I have two questions. Can a transformer be a mapping, a declarative mapping? So like a tuple generating dependency rather than a single query? And this is my first question. And then I have a second question if there is time.
Yeah, so the yes, so I have to, I need to think a bit carefully about the precise definition by what you meant, but in general, the top level queries can be compiled into these these transformers, because there is a construct for key-based partitioning, so it should be possible. So these transformers are meant to be more like an IR or intermediate representation, and if you have a high-level query, then we should be able to map to these transformers. Yeah.
But usually, when you use with TGDs, with the tuple generating dependencies, you might introduce new elements in the schema. So this is the particularity of these mappings with respect to single query, right? Because with a query, the schema stays the same, but with mappings, it can evolve. I don't know if
but the output stream of a transformer can have a different schema.
So then it can be a mapping, yes.
Yeah.
Thank you. And my second question is about this combination of relational time series operators in the workloads. So do you think one can find these mixed workloads in practice or in some existing benchmarks?
That's a good question. So if you look at the standard benchmarks, then they have very little about time series dependent computation. But I think in the future they are going to be more and more important. So so some of the applications we have been looking at are health monitoring. So where you have like a continuous signal, and you want to do operations like smoothing, right, interpolation, and so on. So maybe I have something happening at every microsecond, some reading being taken, and I want to smooth this. So this is not specifiable without this time series dependent computation. And some downstream computation could be using, taking data from different patients and doing some kinds of joints. So the fact that the existing benchmarks don't show this mix that frequently is I don't know if I don't know what's the cause and the effect, right? I mean, I think there are many natural scenarios where you do want to do time series based computation, and so like you are monitoring blood pressure, something like that. So there will be smoothing, you have to detect peaks, you have to detect surges, and then collect data from different patients and do more traditional relational computation. So I think. And the modern machine learning kinds of workloads also show these types of behaviors, right? Yeah. So I think it's actually a deficiency of the current work on relational query processing that they leave out this time series dependent computations because they are wedded to this relational world. And of course, we have made great advances just based on that, but this is more like new opportunities.
Thank you very much.
Okay, so the next question is from Victor Viano, who is being unmuted now and should be unmuted now. Yes, Victor, please go ahead.
Hi, can you hear me?
Yes.
Okay. Thanks a lot for the talk, Rajiv. It's extremely interesting. I have a question about the definition of monotonic transformation. So does it preclude the answer on a prefix to depend on what comes later in the stream? Because it seems to me that there can be examples of monotonic transformations that do depend on what follows.
Yeah, that's a great question. So okay, but there are two aspects. One is what you produce as output tuples, and there it has to be monotonic. So once you produce an output tuple, then you can only add to that. Well, and of course here the addition doesn't mean sequential concatenation, but rather, completing the prefix of this partially ordered structure. Now, in terms of the final value, I think you produce it only when you return, so that could depend on the entire substream. So yeah, I think, but you cannot speculatively produce output tuples because there is no possibility of retracting them, right? Yeah.
Okay.
So you have to store. So in fact, to detect PCARs, I think that's a good example where I have to really store all the, I have to store the tuples I have to produce in the output stream before I can actually add them to the output, because what I do depends on the what happens at the the synchronization marker. So you have to delay the output in many cases.
Mm-hmm. Okay, and related to this, are there or can there be any useful assumptions about memory available to transformers?
Yeah, so that's a great question. So we don't have a good understanding to that, right? So really, so in fact, I think I'm hoping that this is where some interesting research could happen, that you define a class of transformations over these series parallel streams for which you can actually have you have good bounds on the memory, right? And it would build on the existing results on processing sequential streaming data, but coupled with results about how much memory is needed in the streaming setting to do things like joins, right? Where you do make some assumptions about the size of relations that you are going to see, maybe between successive synchronization markers, right? So under certain reasonable assumptions, you get some good bounds on a class of queries. So I think there is an opportunity. So actually, I think the lot of theoretical research in streaming evaluation comes from the algorithms researchers or theory A researchers, where they look at specific streaming computations, whereas we focus more on classes of logics and try to give generic bounds for all queries expressible in that logic. And I think that's possible, but it's an avenue for future research. Yeah.
Thanks a lot.
Okay, the next question is, so Dan has another question. So, should be, yes, Dan, you are unmuted, go ahead.
Yes, I hope you can hear me.
Yes.
So Rajiv, thanks a lot. This was really a great talk. So I have a high-level question. There is a very high bar to adopt a new language. So software developers, they need a very, very compelling argument in order to give up their thing or their trail or whatever they are doing for stream processing. And I was thinking about killer applications, and you did mention this edge computation, which struck me. This could be your killer application. I can imagine that if this beautiful formalist enables the optimizer to automatically decide which computations to push to the edges, depending on what is currently available and what the network traffic is on things that are unavailable at the high level programming language level, that could be a very compelling case. I wanted to ask you if you can speculate, tell us more about your thoughts of where such a system could have a compelling application in practice that other streams processing systems fall short.
Thanks, Dan. That's a very relevant question, and so I've been talking a lot with Zach Ives, who has a very system C perspective on the field and has worked a lot on stream processing data, and he has exactly the same thought that, okay, how do we get people even interested, practitioners and system builders in this, right? And as you mentioned, so edge computing is a great application, and what we have been looking at is actually a system of smartwatches. So actually Samsung had some smartwatches. And so right now, if you look at how, and they have a lot of sensors, right? So the smartwatch maybe has a sensor for, your activities and, your blood pressure. And now in the future, it could even be for your, monitoring your glucose levels and so on, right? So in this setting, the way you program them is at a very low level. You have to program these watches yourselves. And wouldn't it be great if we have a high-level query language where the computation that needs to be done at the watch level could be pushed to the watch, and only when necessary, it will communicate with the cloud. And since preserving battery power is a constraint, you do want as much computation to happen at the smartwatch level. And so now think of a query like you want to compute some health statistics, which can be done locally. But now I want to know that are you an outlier in the current population, right? So maybe maybe now the temperature is maybe you are in Phoenix and the temperature is above 110, and so the statistics have shifted, and you would like to know currently, are you an outlier? So for that, you need to communicate. But can you implement an outlier detection algorithm where the information that you exchange between these watches, or these watches exchange with the cloud, is minimized? And that's where having, I think, a nice query language, where the compiler pushes computation to the smartwatches only as needed, would be quite useful. So you are absolutely right. So the edge computing in a resource-constrained environment is a potential application, right? Yeah. So but as you said, the bar is super high because this is a fast evolving space, and all the commercial players have their own stream processing systems. Yeah.
Okay, so we have a question on the Q&A by Tianyu Chu. I'm allowing him to talk. Wait. And did it work? Yes.
Okay, but I can see your question. So
the question is, does this apply to graph data? Can this be used for graph data? That was the question.
Yeah, that's a very good question. Not directly, yeah. So because even though the data here is kind of partially ordered, which is really a graph, but the dependencies are expressed using this schema, which is static, right? So you are saying that the typical constraint we're expressing is that the GPS events of the same taxi are ordered, and the GPS events of the different taxis, they have no edges in between. When you think about computing with graph data, the data itself is specifying, the edges, and this particular framework, at least, there is no direct way of applying it. Yeah.
Okay, I have a quick question myself, a little bit more technical. So at some point in the early part of the talk, you basically mentioned we have this synchronization schema. Oops, sorry, some people decided just to drive their motorbikes outside my window at the moment to ask the question. So so if you have any linear sequence consistent with your series parallel POSET and with the POM set, and you have the schema, then you can uniquely recover. It, right? Since this is a bit puzzling because we know, of course, that every series parallel POSET is just it has order dimension 2, so it's intersection of 2 linear orders. So I can represent each one as 2 linear orders, and you're telling me that no matter which linear order is consistent that I take, I can infer the second one that gives me the right series parallel POSET here, just from the schema, right? Just wonder if you have any comment.
Yeah. Because right.
To me that look quite puzzling. It somehow encodes lots of, it means it encodes tons of information, and I'm just trying to get an intuition for that.
Oh, right, because the schema actually tells you, how the which edges exist and which edges don't exist, which is not the case for an arbitrary series parallel graph, right? Because the label, so there is in general, for a series parallel graph or any partially ordered graph, there is no constraint on what labels go on these vertices, right? Whereas here, we are putting constraints, right? So, for example, when I say the schema is S parallel S prime, well, just the label tells me whether it's part of one graph or the other, right? So it's really it's very strongly typed, basically. And those types dictate what kinds of labels can appear on these different vertices.
All right. Okay.
Yeah.
Okay, so we are done with questions. So before we wrap up, I would like to remind everyone here that we have a PODS business meeting, which starts in about 42 minutes from now. And everyone is welcome to attend. And now let us thank Rajiv one more time with a big round of virtual applause for this very interesting talk, given twice live to us, and hopefully we'll see more follow-ups, and I also hope to see more of Rajiv in our community. Great, thank you very much, Rajiv.
Yeah, thank you, and thank you for this opportunity to talk to PODS folks.
Okay. Thanks. So now it's a break, and then people interested in the business meeting. So I'll see you in about 40 minutes from now. And I guess it's up to the organizers to...
Yeah, we don't have the right to close the webinar, but...
Okay. Yeah. Thanks, Roger. That was nice. That was very nice piece of work, actually. I was absolutely not aware of this. So...
Yeah, thanks. Yeah, no, I mean, this is very new. I mean, this is the first, the first paper is really in PODS that we sent, and and I'm glad there were a lot of questions, and I'm hoping that some of the people will get interested in this, and so, but particularly about this, how to define good logics and transducers over these structures. I think there are many people in the PODS community who know who will have great ideas about this. Yeah.
Mm. Yeah. Okay. Good.
Okay.
So
thanks. Yeah. Thanks.
Get a bit of rest. Recover your voice.
Yeah. Okay. So, yeah. We'll talk to you later. Okay.
Okay.
Thank you very much, Rajiv.
Thank you.
Bye-bye.
Bye.
Thanks. Bye.
So, Leonid, see you in 40 minutes. No, in 30 minutes.
Just even a little bit less. Yes. So just want to. So I'll let you. So you'll be the panelist. So you'll share both you and I would assume that both you and Pablo will share the screens.
Yeah. For the report, I mean, sure, you are the session chair, but you will tell us when we should.
Yes, I'll tell you when.
Yeah. I would hope. I mean, it's no problem if Pablo might possibly not automatically have panelist rights, but then it's up to us to promote him. And
we can promote somebody. Okay.
Anybody, you can promote also everybody. If it's a small group, it's a nice atmosphere. If everybody is panelist and turns on the video, in fact. But it's your decision.
Yeah. Can we also give people virtual beer in Zoom? I guess that's how.
No, I think everybody has to take care of analog beer himself, herself, which I will definitely do. Yeah. So after my report,
I will not do it until after the session.
Yeah. Now I'm already up since a bit. I had my alarm clock a bit ahead of 3 a.m. So I will definitely have to skip the rest of the program after that.
Yeah, the last week I had those ISO meetings, which were
and in between, as I saw, you answered a couple of emails.
Yeah.
Oh my God. But
yeah,
I mean,
like 3 days in a row from 6 to 9. No, actually, this time it was 7 to 10, thanks to winter, because last time it was before we switched to summertime. It was 6 to 9.
Oh, I see.
Cool. Next week it's 3-hour sessions, 11 p.m. to 2 a.m. Which is okay. Last time it was not okay because then my daughter was getting up and going to school at 6:20. So when you finish your meeting at 2 in the morning, and then at 6:20 their alarm clock in adjacent room. Yeah.
Okay.
Yeah. Too much Zoom. Anyway, okay, I'll see you in half an hour.
Have a short rest and we meet again in half an hour.
Yeah. All right, see you.
Bye-bye.